Good morning, everybody. Well, it's November 28th and we're past the Thanksgiving break. I hope yours was great. We're not going to have time to do the usual unit that we do afterwards between the move and finding equipment and all of that. What I'm going to do instead is add this to Unit 3. It's pretty interesting stuff, and there'll be 2 days. So we finished with the ideal gas law on Friday, and now we'll beginning, on last Tuesday, and that was really the end of the gas unit. And now we're going to talk about how do the particles get to the gaseous state of matter to begin with. And so that leads right into this. All right, the essential questions. How do a group of particles change their state of matter? So we've seen this picture many times of particles in the gaseous state so close together and in military formation, very attracted to one another. That's why they can only move up and down to the right and the left together. Then we saw that in the liquid state, something happens with the arrangement of the particles and they move farther apart. So we're going to be talking about how does that happen? Why does that happen? And then we know that the gaseous state of matter is totally unlike the others, and the particles are very far apart. The particles are moving much faster. The particles act like they don't annoy each other. And we talked about the fact that the particles in a gaseous state become less ideal as they move towards condensing into the liquid state. So we'll talk about what those conditions are a little more. All right, but nearly every element on the periodic table occurs in the solid, liquid, and gaseous state. But many of the elements on the periodic table we know only in really one state of matter because that's what they occur in the range of temperatures that occur on Earth. So between the temperatures that we commonly live at, what are the state of matter of these materials? And that's the one we know. But in fact, nearly every state, nearly every element, nearly every compound can exist in the solid, liquid, and gaseous state, depending on what the temperature is. All right. Secondly, how can we tell what happens when a group of particles changes state of matter? Simply by measuring the temperature over a period of time. So we know it has something to do with temperature. The third thing is, oh wait, let me talk about this. One other thing is I'm relying on your previous knowledge. So we know that states of matter occur because we've experienced many of them in our daily lives. All right, we know things vaporize. We know liquid gas vaporizes, for example, because we smell it. Or anything we can smell, there's vapor particles in the air. And we're going to talk a little bit about those vapor particles and the pressure they cause a little bit later. Now, the second thing is, what do the experimental graphs tell us? So, what I'm showing you is how chemists would deal with this problem. So, normally we would spend a day doing this experiment. But today, instead, we're going to pretend that we've already done the experiment and we have the graph. Now, the graph is going to look something like this, all right? All right, notice what we have on the y-axis. Notice what we have on the x-axis. All right, when you look at this substance, see if you can tell what this substance is. Just give it a look now and see if you can tell what the substance is now, and if so, write it. Now remember, as we're watching this, I want this to only show on your side of the screen, one side of the screen, and that your paper is on the other, so you can be writing. All right, remember, you get the points for writing on your own paper. All right, so have you done that already? Do you have what I'm showing you on one side and then yours on the other? The last question is, what does a heating or cooling curve for water or any other compound or element tell us about the change of state? All right, now we want to get to the scientific ideas behind the involvement of change of state of particles. What are the scientific concepts that are important for us to learn from a very simple experiment such as this? And you'd be surprised how many there are. All right, let's go into it now. Number one, how do a group of particles change their state of matter? All right. So we know what the pictures look like. Melting requires heating. Tell me if you don't know that. Each solid has its own unique melting point. All right. I believe you definitely know that. So the melting point is the temperature at which the particles in the solid are using the heat to rearrange because they're moving faster and break attractions. So essentially they're going from this, all right, to this. All right. They're still very close together, all right? But they are not in a uniform arrangement like they were in the solid state. So this is the most common arrangement for elements in the solid state. Compounds a little less so just because they have more unique shapes, but they are very close together. And in the liquid form, they are clearly moving apart. All right, that's the temperature at which the particles in the solid are using the heat to rearrange. All right, so that means that this is going on. That in order for that to happen, to go from a solid arrangement to a liquid arrangement, we need heat. All right, so they're using the heat to rearrange. Because with the heat they move faster, and the increase of the speed allows them to break attractions. Freezing requires cooling. I know you know that as well, right? You just haven't maybe thought of it in those words. So liquids have a characteristic temperature at which they turn into solids, which is known as their freezing point. So in theory, the melting point of a solid should be the same as the freezing point of a liquid, correct? Liquids freeze, solids melt, but it should be at the same temperature. All right, and that's called cooling because when we put water in the freezer, we are essentially taking the heat off of it, right? All right, in the cooling process, there is heat that is being removed. All right, so cooling is heat being removed. So both heating and cooling involve the concept of heat. I do. My husband's in here bothering me. All right. Boiling requires heating. Oh, I know you know that because you have to heat water on the stove to make it boil, right? Isn't it amazing how much you know? Even before it boils, liquids have vapor because some of the particles are going so fast and separate from the main group of particles. So remember when we talked about kinetic energy, we said that the average kinetic energy is the same of all the particles. Average. But some of the particles are going very slow because they're changing directions after they hit the wall, and others are going much, much faster. All right. So it's these super fast particles that are able to separate from the main group of particles and go into the vapor state. So we call them vapor. The number of particles in the vapor that are pushing on the liquid surface is called the vapor pressure of the liquid. Vapor pressure, all right, of the liquid. I know it's an odd term, but you know that vapor means gas, right? When gas vaporizes at the gas station, we can smell it. All right, so anything we can smell like that is in the gas phase. But gasoline is liquid when we put it in the tank, isn't it? So because it boils at a very low temperature, we are often near the boiling temperature on a hot summer day. We can smell a lot of gas. All right. Even at room temperature, liquid water has a vapor pressure. Now that's maybe a little bit shocking. Let's find a, yes, That's maybe a little bit shocker because we think, well, it vaporizes when it boils. But no, even at room temperature, liquid water has a vapor pressure. And we can see bubbles forming when we heat water, right? You can always see those little bubbles of water. All right, you maybe don't know what they are, but they're just water. They're water vapor. We know bubbles are gas, right? As the liquid continues to be heated, its vapor pressure gets higher and higher until it's the same as the air pressure. What? As the liquid continues to be heated, the vapor pressure gets higher and higher until it's same at the air pressure. Oh. Oh, the vapor pressure of the liquid gets as high as the air pressure surrounding it. That's when boiling occurs. Oh, so when the vapor pressure it gets higher and higher and the same of as the air pressure, that's when we see the rolling boil at the boiling point temperature. All right, so until then, the temperature's increased and we've gotten more and more vapor. But it isn't until we see the rolling boil of all those bubbles that we've reached the boiling point temperature. All right, and the temperature remains constant. What? Until all of the liquid has been converted to a gas. Oh, the temperature doesn't keep rising? The temperature remains constant until all of that liquid water at the boiling point temperature has been converted to a gas. Oh, well, that's a new idea. Did you think that whenever you heated things, the temperature would just continue to rise and continue to rise? And this is telling you that at the boiling point temperature, it remains constant, that temperature, until all of the liquid has been converted to a gas. New concept. New concept. All right, we should mark that. By definition, then, a liquid boils when the vapor pressure of the gas escaping from the liquid, all right, is equal to the pressure exerted on the liquid by its surroundings. All right, I didn't show you in that figure. All right, the pressure exerted on the liquid by its surroundings, and that's air pressure, right? Chemists are always thinking about the air pressure that is around us, and it's going to be very close to 1 atmosphere, right? 1 atm. All right, I got that from ChemEd Purdue, this quote. All right, now the normal boiling temperature of water is 100 degrees Celsius. All right, so originally thermometers were made from 100 to 0 because this temperature was the boiling of water, and this was the melting of water or the freezing of water. All right. And so that's how they created the temperature scales. That's why it's called centigrade. Centigrade means 100 degrees between boiling and freezing. All right, so that's how they set up the first thermometer. And then they graduated it. So if there's 100 degrees between these, then they just graduated it in tens all the way up and then ones. So that's how the original Celsius thermometers were made. And then they extrapolated above 100 and below 100. Excuse me, below 0. All right. Now, I talked about this the other day. It says the normal boiling point of water is 100 degrees C, all right? And all over the world, that's true, except we think in Fahrenheit. In Fahrenheit, this is 212, all right? In Fahrenheit degrees. But if you try to cook an egg in boiling water while camping in the Rocky Mountains at an elevation of 10,000 feet, you'll find out it takes longer for the egg to cook because Water boils at only 90 degrees C. So while you're cooking something in water, you can't get the temperature higher than 90 degrees C. Water boils at a lower temperature when the air pressure is lower. Why? Because the vapor pressure of the water reaches air pressure faster. Remember I told you that in Laramie, Wyoming, at an altitude of 7,200 feet above sea level, I was unable to get rice cooked. That's because of when the water boils closer to 90 degrees than to 100 Celsius, food takes longer to cook because that boiling temperature is lowered. Aren't we mostly cooking food in water when you think about it? Even in microwaving, the microwaving is heating the water molecules in our food. Now, I know you've heard of a pressure cooker. It does the opposite of what was happening in Laramie. By increasing the pressure over the food, the boiling temperature of water is much higher. Why? Because the vapor pressure of the water doesn't equal the pressure inside the cooker until it's closer to 120 degrees Celsius. Can you believe? Wow. So these days, Instapots, I know many of you have Instapots. They replace it means instant. Instapots replace pressure cookers because they also cook with higher pressure and higher temperature steam. So the food is cooking in the steam, the water and the steam generated by the higher pressure cooker. Instapots are also electrical rather than the stovetop, and they have been engineered to be safer than the old pressure cookers. Yeah, safer over time. So I bet many of you have Instapots. We do too. Condensing. We've talked about boiling, right? Now, condensing requires cooling. Particles in the gaseous state of matter condense. Oh, when they get too close together, remember? Oh, we said that's when gases that were supposed to be ideal become a little trashy. I made that up. All right, it's because they get too close together. That happens when the temperature drops and the particles slow down. So if that continues to happen and the temperature continues to drop and the particles continue to get closer together, that's when condensation occurs at whatever the boiling point temperature of the substance is. Whatever the boiling point temperature of the gas is, it will condense at that same temperature. All right, so this relates directly to what we talked about. The ideal gas condensation occurs when the temperature drops and the gas particles get close enough together to be in the liquid state. So instead of being like this, all right, the temperature drops and they are like this again. And then they are ripe to become a liquid. The second, how can we tell what happens when a group of particles change a state of matter? Simply by measuring the temperature over a period of time. You will be a little shocked at how easy this method is. All right, so look at a typical experimental graph below. All right, when you look at this, all right, we see that they're the typical axes, and we see that there are slopes of a line, correct? But instead of it being a straight line slope or even a curve like this that we've experienced before, we're seeing something different, aren't we? We're seeing a diagonal line, a straight line, a diagonal line, a straight line, a diagonal line. So diagonal means it goes up at an angle, but it's straight, correct? So we could measure the slope of this line. We could measure the slope of this line. All right? And then we have these places here in which the slope is 0. And when you look at it, what isn't changing? What isn't changing at these points? So when you have a horizontal line, it means one of the variables is changing, but the other is not. So I want you to look at this and see what variable is changing when it's horizontal at this point and what variable is not changing. That's why we have a zero slope. The change in y over the change of x is zero. All right, so what variable is not changing? Think about that. Now, what I want you to do is reproduce this graph right over here. When you reproduce it, it doesn't have to be as perfect as this is, but I want you to draw it in your own with your finger. You can make this as big as you need to. All right, and it doesn't have to be perfectly like this, but I want you to indicate what's going on over here, and then I want you to draw the lines. All right, so let's stop this video now so you can do that. All right, get busy drawing with your finger if you don't have a stylus. I'm thinking 3 to 4 minutes. The purpose is for you to assimilate this graph better into your memory. All right, number 3 says, describe what you observe about water from the graph. So now that you've drawn it and you realize what's on the x-axis and what's on the y-axis, you can fill this out. All right, so go ahead and fill out right here what variable is on the x-axis and what variable is on the y-axis. Next, we saw that the lines were a bit odd because there wasn't just a straight line like we'd grown to expect, nor was there just a curve. There was a mix of diagonal lines and horizontal. So explain what it was you saw, like perhaps give them an order, like did you see the diagonal lines together? Did you see the horizontal lines together? Did you see them mixed up? What did you see? All right, now the pattern of lines. I want you to draw the pattern of lines here that you saw. All right, go ahead and do that now. I left you lots of space to do that. We talked about the shape of the lines as being horizontal and diagonal, which is a combination of horizontal and vertical, isn't it? Horizontal meaning flat, vertical meaning up and down. Draw the pattern of those lines. And then with the description of the graph, why do you think this graph is called a heating curve? I mean, to us it looks like a graph, except clearly it's not like any typical graph we've ever seen. Why is this graph called a heating curve? It's not really a curve, is it? Why is it called a heating curve? All right, look at what the intent of the graph is and fill that out. We'll stop the video so you can do that. Now, part 4 is, what does a heating or cooling curve for water or any other compound or element, a heating curve for a compound? There's heating curves for elements. We just picked the easiest thing, which was water. Yes, and because we see that in 3 states of matter routinely in our life. All right, so what does a heating or cooling curve for water or any other compound or element. So we're able to generalize beyond water. What does it tell us about the change of state? All right, so from the heating curve, I want you to answer the following questions. So, the question, what is happening to the water particles? So now we're going down to the particle level, aren't we? So this is really question about particles, because we're concerned in the particle model about everything that happens in matter. What does that say about what the particles are doing? We use the explanations at the atomic level to explain what's happening at the level we can see. So the first question about the particles is, what's happening to the water particles when the lines in the graph are diagonal? All right, so we've had a chance to think about this. So what it's saying, so find the 1, 2, 3. There's 3 diagonal lines. So this question is asking, well, look what's happening at each of those, and what do they have in common, these diagonal lines? What do the diagonal lines have in common? All right. Yeah. What do the 3 diagonal lines have in common to show you? All right. And I'll make that pretty tiny. All right. So answer that now. And we can stop the video. Secondly, B asks, what is the heat taken into the system being used for in these diagonal areas? All right, so the question is, what is the heat doing? Why do we heat? Why do we heat? So another way to say is, why do we heat water? All right. So what is the heat? What is the heat providing us? All right, what is the heat providing us? So we'll stop a second and let you analyze this. Now remember that it's not just facts. I mean, you learn plenty of facts, but I'm wanting you to exercise your thinking about the facts we're learning, because, as I've told you many, many times, helps you to remember it. Memorization is such a partial memory process. But when you understand something, you have it in a context related to other things. So when you pull it up, you pull up a lot. You may even pull up this whole graph in your memory to help you explain what it is you know. All right, C. What are the melting and boiling points of water according to this graph? All right, remember that we use experiments to help us learn facts. And one of the facts here that we found out is, what did the melting point of water appear to be in our experiment, and what did the boiling point of water appear to be? How did you know? How did you know? I know the melting and boiling, melting point of water is, and the boiling point of water is, because in the graph, yeah, All right, so that's what I'm wanting you to do. Remember, I never just want the answer because I already know what the answer is. Yeah, so it doesn't help me to know that. It only helps me to know what you have learned. All right, that's what I want you to tell me. Now let's go down to D. It's talking about what's going on with the water particles when the places on the graph are horizontal. All right, so now we look up at the graph here, and it is related to the last question. What's going on when the graphs, we have two of these showing, when the part of the graph is horizontal? It's asking you what's happening to the particles. What's happening to the water particles when the places on the graph are horizontal? What's happening to the water particles? That's the key here. What's happening to the water particles when the places on the graph are horizontal? So I don't want to know what we've said before. I want to know now what it means that we have a horizontal line. What does it mean that the line is horizontal? All right, that's what we're wanting to know here. That's what I want you to explain to me that you've learned as a result of this. All right, that's what I want to know. Let's make that smaller so you have plenty of room to write. E says, what is the heat taken into the system being used for at the horizontal areas? So once again, we knew the heat before was being used to raise the temperature, correct, of the water. Because we always have to do that when we're melting or boiling. But now, what is the heat taken into the system being used for at the horizontal areas? That's another issue entirely. All right? Big question. You probably have to talk to your partner about this. All right, now F. Now, I've shown you a heating curve. Now what I want you to is draw a cooling curve of water. Oh, that's not a question. That's an expectation. So I want you to start with steam at 120 degrees. So we'll start up here, right? And end with ice at -20 down here. So I changed this axis to say amount of heat released because cooling, remember, is not about adding heat. It's about getting rid of heat. All right, so now that's what I want you to do. So go ahead and finish that. All right, work on that. Do a good job. This will really show your understanding. So work with your partner on that if it's unclear. Once you get started, you will suddenly realize what you have to do. So don't just sit there, try and start. What would be happening at 120 degrees? Go.